to the Suns and Planets session. Just a quick programming note. The second talk is going to be given by Candace Gray instead of Sarah Kovac, but the title will remain the same and the content will be what you're expecting. So with that, let me turn it over to Derek Buzasi from Florida Gulf Coast University. His title is A Self-Consistent Sample of Solar Analogs. There it is. And I am going to try to do my background video with the timer, just so you'll have a sense of where we are with time.
Okay, sounds good. All right, good to be here. I'm a professor at Florida Gulf Coast University, and I'm a leasing partner. We are a leasing partner with the observatory. So I want to talk today about a project which is a work in progress, which is building this self-consistent sample of solar analogs. And I want to go through this by first talking a little bit about why maybe you should care about solar analogs when you maybe thought you didn't have to, define kind of loosely what I mean by a solar analog. That's a rabbit hole we could go down for a long time, so I will just brush it lightly. I want to talk a little bit about measurement of one particular parameter, rotation, and then talk about how I built the sample that I'm working on now and how the Apache Point Observatory is contributing to the project, and then kind of update you on where we are. So here's a very, very short introduction. So, I mean, looking at solar analogs essentially arose from the idea of trying to understand the sun better. And so we have sort of two complementary approaches. One is to look at the sun itself in detail and try and infer from that behaviors of stars. And the other, of course, is to look at stars that are like, but not exactly like the sun and use those to infer solar behavior. So as I said, we can kind of go down a rabbit hole with what solar analogs are, but if you just kind of keep in your mind that they are solar-like, that will get you into the ballpark. Exactly how solar-like is one of these things that's sort of the solar stellar community's analog to, you know, what is the value of H naught anyway? And we can have, you know, large fights about it, which don't mean anything to anyone outside of that particular community, but just keep that in mind. People talk about analogs, which has a very vague definition, and people talk about twins, which are stars which are much more solar-like. The stars, my definition of analog is much closer to what most people would call a twin. So the stars I'm talking about are very solar-like. Something to keep in mind, which I'll come back to later again, is that, you know, you can't be too precise or too demanding about what you expect from an analog. And part of that is because, of course, some parameters we can't measure that precisely. And part of it, of course, is that there's an envelope of solar characteristics and behavior. So if you are picking stars that are like the sun in terms of activity, well, you know, do you mean the sun at solar minimum, or do you mean the sun at solar maximum? So you have to be careful not to demand too much of these things. So why look at solar analogs? Well, I mean, it might be that you're interested in the sun and the solar system, so then they can shed some light on composition, structure, activity, evolution, et cetera. They can be nighttime proxies for the sun. That turns out to be relatively important because simple parameters that you'd think we would know pretty well, like what is the B minus V color index of the sun, there's not actually a really good answer to that question, or maybe more precisely, there are many answers to that question and they are not all the same. Part of the problem, of course, is that we look at the sun with different instruments typically than we look at the stars with. And a more fundamental problem, perhaps, is that we look at the sun in the daytime and we look at everything else at night. So that does create problems. You know, it can give us, looking at analogs can give us snapshots of the evolutionary dynamical history of the Milky Way. We can learn about, if you're interested in planets, we can learn about abundances maybe in planet formation. We can learn about habitability due to solar and stellar activity. We can learn about dynamos. And I think most fundamentally, we can treat these things as laboratories. And what I mean by that is, you know, I tell my students all the time that one of the things that's sort of different about astronomy from a lot of other sciences, not all of them, but certainly many of them, is that we don't generally get to do experiments. And so this is sort of a substitute for experiments, right? So if I want to know how rotation affects what's going on in the sun, maybe a good way to do that is find a bunch of stars that look like the sun in every way except rotate at different rates, and use that as my sort of naturally occurring laboratory. So lots of reasons I think that these are potentially useful. Surprisingly, there are not a lot of good samples. You know, I listed some studies here But basically the idea with the problem with some of these is that people either measure photometric activity very precisely, but don't do spectroscopy, or they measure spectroscopy and they don't do photometry at the same time, or they do seismology, but not other things, or they measure abundances and they don't measure activity. So it's really difficult to find a sample that is large. And you want a large sample because we want to be able to look at how different physical parameters vary across that sample, and a sample which is kind of coherent. So the idea here is to try to fix that, to find or build a sample that satisfies these things, and has more than 20 or 30 members in it. So how do I define an analog? Well, I mean, there are, of course, many ways. So one might start with things like color index, which are relatively easy to measure, rotation period, right, which is, again, sort of easy to measure, although we'll come back to that, or the spectroscopic analogs of V sin I and things like that. You might do spectroscopy and get an effective temperature. If you're really lucky, you might have other tools at your disposal. But of course, this is a tiny piece of this sort of huge envelope of things that we could actually be looking at when we talk about solar analogs. And so some of these are relatively easy to measure, right? Color index. Some of these are hard to measure, like magnetic field. Some of them are, we hope, constant, certainly over human timescales, like mass, and some of them, like activity, are not constant. And some of them are empirical in nature. So if I measure the rotation period, hopefully, if we all measure the rotation period, we get the same answer. And some are model dependent, right? I might be interested in the mixing length, but that's going to depend on, what kind of model I'm interpreting my observations through. So there are many things that we can go and look at, and we're not going to be able to define a solar analog in terms of all of these things. So we have to sort of specify what it is that we're focusing on. So I just want to emphasize again, we want our parameters to be close to solar, but not too close to solar. So on the left is, I wouldn't call it a solar analog, but some people would. It's a G subgiant. But this is the Mount Wilson S index as a function of time. And you can see, again, just like on the solar case, if we measure at low activity, we get a very different value than if we measure at high activity. So if we're going to specify what solar-like is, it's really an envelope of behavior that we're talking about and not a specific value. The same thing's true if we're measuring things like in the center figure here, the solar irradiance, which is harder to measure for other stars, but say spot coverage, which again varies a lot as a function of time. So certainly, a star that's got 10% spot coverage probably isn't very solar, but there is a range of values over which we could reasonably call something a solar. And on the right, I have rotation, which I'm going to take a detour and talk a little bit about, because rotation is, one, hard to measure, and two, it's not, what is the rotation period of the sun? Well, it depends on what latitude you look at. So I don't know what the right answer is. If I put a spot, if I'm going to measure rotation with spots, it depends on the latitude of the spot. All right, so here's exactly what I was talking about. So we measure rotation typically photometrically. We look at spots. We watch them rotate. We don't get to see the disk like we do on the sun, but we watch the star rotate as a function of time. The star gets brighter and fainter, and we infer from that what the rotation period is, which sounds really easy when I say it in one sentence, but in practice is not that easy. So here's an example. At the top is the solar case from SOHO, from space. And you can, if you look closely, you'll see there's actually two lines there from two different filters, but they mostly agree with one another. The variability, you get a nice period out of it. The variability is like 0.1%. On the bottom, we have a stellar case, also from space, from K2. You'll notice that the variability is much larger. It's a couple of percent instead of 0.1%. It's hard to measure small signals, so we have some biases in there. And also in the case of K2, we only have 80 or 90 days. So we really only see, in this case, 3 cycles. And there's also a red curve and a black curve there. And this is sort of the dirty little secret about what's, our ability to measure rotation periods. Those aren't two separate measurements. So here's the problem. So this is, if you look closely, and I apologize for the print is rather fine, but the takeaway here is that these 5 panels are all the same star. And in fact, they're all the same star and the same data set. What this represents is 5 different pipelines producing light curves from the same K2 data. And this is a star with a rotation period of around 4 days. And in fact, all of these would agree with that. They would not all agree on what the amplitude of photometric variability is. There's a almost factor of 2 difference between the smallest and the largest. So this is something we need to worry about a lot. How do we handle the fact that different pipelines give us different light curves? And which is the right one? We don't know, because there's no real ground truth for this. We also have different ways we can measure rotation periods, right? So there's, autocorrelation and Lomskargel and other techniques. And again, they give us, in this case, more or less the same answer, but not exactly the same answer. And as periods get longer and amplitudes get less, they give us less and less the same answer. So what's the solution here? Well, my solution is to use many pipelines and many methods. So I take 5 or 6 different pipelines, I try 5 or 6 different ways, and so I get 25 or 30 different periods, and I look for periods where there's consistency. So what's the sample that I'm working on? You might have guessed it's a K2 based sample. I like that because we have photometric variability to start with. We have rotation periods, at least in some cases. We have fairly long time baselines compared to TESS. They're relatively bright stars and they're broadly distributed over the ecliptic. So when we finish with our sample, we'll have something that other people can use. So I initially built it based on photometric colors, which gave me 2,000 stars. I then trimmed it based on literature values for effective temperature and metallicity and log G, a box basically plus or minus 1 sigma. Not that the published values are really, those errors are definitely understated. I required that I got non-anomalous light curves from all the pipelines I'm using, so I could actually compare them to each other and then cut down to bright stars, V less than 10. And that gave me 181 targets. So here's one of them. You can see in the center the outputs from 5 different pipelines, some of which look better than others. As a side discussion, we can argue about which one is best. There's not really an answer to that. A bunch of different periods. And then when we look at all of the periods together, we have some sense at least of what the systematic error is. So again, in this case, about a 2-week period. So I'm using the ARC, the 3.5 meter, to do spectroscopy of all of these stars. So to date, it's 28 half nights and 129 unique stars. And the idea here is that we have a uniform sample taken with the same instrument, all of these candidates. And then I'm, among other things, using this Yi Pettigura empirical spec match code, which essentially takes a set of stars with high res, high signal noise spectra, and very well understood parameters defined by some touchstones. So the stars that we're comparing to are eclipsing binaries, or have astroseismology, or have interferometry, or have more than one of those things. And then we essentially build a composite spectrum out of the stars that have spectra that are closest to it, and use that to infer what the physical parameters are like. So in this case, not too bad, fairly close to solar. I'm almost done. And then we do use the same spectra to do the S-index measurements, so we get at least a snapshot of activity as well. All those are combined with archival data analysis and archival values of rotation periods, Gaia parallaxes and colors and derived quantities, other space-based colors, archival spectra wherever I can get hold of them, archival activity data when it exists from the Solar Stellar Spectrograph or Mount Wilson. And that, to date, is the sample, so it does span the sky quite nicely. It makes it relatively easy to set up an observing program because there's always something up. But the idea is that we will build a collection of solar analogs that are accessible to any observer pretty much at any time. So there's the takeaway, and I'll stop reading it so that I don't go over time even more. Happy to take questions.
Thanks, Derek. That was great. Do we have any questions from the audience? If not, I will ask one. John, please go ahead.
Yep, sure. Really nice talk, Derek. In terms of calibrating and assessing the different pipeline results, is there any hope of using systems with known parameters like binaries where you might have spectroscopic confirmation, for example, of their periodicity and color variations?
Sure. The problem typically is that, if you have stars with short, if you're looking at rotation periods, if you have stars with short rotation periods, so 4 days, like the example I showed, you get the same answer within a few percent from any pipeline that you choose. The problem typically comes with the stars that are slower rotating, which are sort of more solar-like, right? I mean, the sun's rotation period is nominally around 25 days. 25 days is really hard, and it doesn't matter what kind of pipeline that you're using, and you get very, very different results for different pipelines, and those are stars for which we typically don't have any other way of measuring them or any kind of touchstone that we can compare to. I mean, I showed examples where they looked kind of similar, but I mean, there's outputs for a couple of stars, and they can look hideously different sometimes, and trying to figure out what the what's really going on and what the right answer is really difficult.
Yuta, go ahead and ask your question if it's relatively quick, and then we can keep the conversation going in the Slack. Thanks.
Okay. Quick question. Do you have a plan to measure S-index long-term variations?
I am not measuring long-term variation, but I'm happy to contribute the data to anyone who's doing that. I mean, this is more snapshot plus archival, mostly because I want to be able to define an end to this project. It's been going on for a long time already, and if I switch into the archival mode or into the long-term variability mode, it's going to be another project that I'm involved in that's going to run for 20 years. I'm trying to avoid that, but certainly the data are available.
Nice.
All right, thank you. Great, so let's move on.